This is a video intended to showcase the technical aspects of my master's thesis. Specifically, how the user interface works, how the sign language recognition system works, and what were the findings from the study. Let's begin with the user interface. The user interface is comprised of two parts, a repeating part and a non-repeating part. When the user first starts the application, the UI state moves from loading to welcome. Here, the user must raise their hands to continue. This was done to verify that the hands were tracking properly. When this is done, the user moves out into the repeating part of the system, starting with the prepare state. Here, the user is shown what sign to perform, allowing them to prepare. To engage the SLR, the user simply raises their hand towards the screen. This system with the icons is referred to as the hand gate. As the user enters the write state, the system begins to perform recognition on the user's virtual hand before automatically moving into the result state after exactly 2 seconds, and then back to the prepare state again after another 3 seconds. These states were all implemented using flow graphs in the Unity editor. The user stays in this loop until all sampled sentences have been trialed before exiting, but it is specifically in the write state that the SLR system operates. So let me explain how that works. The SLR system consists of 3 different subsystems: the language model, the gesture model, and the fusion approach. The language model is executed in the beginning of the write state, while the gesture model and fusion method runs at the very end of the inference window. The purpose of the language model is to contribute knowledge about the spelling context to the final prediction. This model was trained on an open source dataset of more than 7,000 sentences using an n-gram linear classifier. The training data was filtered and the performance of the model was validated for different values of n, along with different permutations of the input data. The classification performance of this model in isolation was approximately 54%. The purpose of the gesture model was to contribute knowledge about the performed gesture to the final prediction. This was achieved by computing the Euclidean distances of each individually tracked finger bone and a pre-encoded target and scaling the length of this vector based on the movement of the bone. Finally, the purpose of the fusion method was to combine the predictions from these two models. This was done by defining a constant value, which was then used to scale the influence of the language model depending on how uncertain the gesture model was about its prediction. In the end, the model performed significantly worse than the state of the art, and it was concluded that the use of a language model for context injection was not enough to achieve one-shot gesture learning. However, if the language model and the gesture model could be revised with more sophisticated approaches, then the use of a fusion method to combine the two may still be a promising avenue for further research in this field. Thank you for your attention.